Okay, this is a quick tutorial intended to walk you through how to use the solver function on Excel to solve Michaelis-Menten kinetics and determine the Km and the Vmax value. So you'll start off with a spreadsheet that has the substrate concentration versus the initial velocity. Okay, so if we plot this, we're going to see the normal kinetic trace that we would expect. Okay, so here we're plotting our Michaelis-Menten kinetics. So our goal is to first approximate what Km and Vmax are to give us initial estimates, and then we're going to actually determine what the best values are that fit this experimental data. So first things first, let's start off by putting in a spot for Km and Vmax that, maybe. So first things first. Let's go ahead and put in a cell for Km and Vmax and approximate these values based on the experimental data. So what we can see here is that our Vmax is tending towards about 70. So if we just estimate our Vmax at around 70, that might be a reasonable guess. If our Vmax is 70, then 1/2 Vmax is 35, and our substrate concentration when we have 1/2 Vmax is around 90. So our original guess for our Km value is 90, and our original guess for our Vmax is around 70. Okay, so what we want to do now is using these guessed values, using these estimated values, we want to go ahead and solve for what the experimental V0 should be if these values are correct. So we know the equation is the initial velocity is equal to Vmax times the substrate concentration divided by Km plus the substrate concentration. So we're just going to put that into our Excel cell. So equals indicates an equation. We want to have the substrate concentration for the first sample times our Vmax divided by, make sure to put parentheses, your Km plus your substrate concentration and close your parentheses. So if our Km and our Vmax are right, then when the substrate concentration is 30, then our rate should be about 17.5, which really isn't too far off from what the experimental value is. So to make this easy, let's go ahead and put in $signs to tell Excel not to change I7 or I6. So as we vary the row number, we're not going to be varying these numbers. And then we'll go ahead and drag this down, so copy that equation to all of these cells. Okay, what you'll notice here is as I move from cells, I did change from F12 to F13, but I did not change from I6 or I7. Okay, so that's just a quick calculation. The next thing we want to do is figure out how good this approximation is. And the easiest way to do that would be to take the difference between the calculated value and the actual value and square it. Okay, so we're going to do equals, open parentheses, I want to do the actual value minus the calculated value, or vice versa, it doesn't matter. And I want to square it so I don't end up with negative numbers. And then I'm going to go ahead and copy that all the way down. So to give me an estimate of my goodness of fit, right, so how good the estimated calculated values are, we're going to go ahead and sum these up. So the Excel function is sum, and you can choose the whole area. And I like to take this times about 1,000 just to make sure that I really magnify the differences that we see between the experimental error, between the experimental values and the actual calculated values. Okay, so this is an important cell, so I'm going to go ahead and boldface it. So this is what we want to minimize when we're playing around with our Km and our Vmax. Okay, and just to kind of show you what this might look like if we plot it, so I'm going to go ahead and replot this. So insert, I'm going to put in a graph here, and what we can see is that the estimated values, which we have here in the orange dots, are pretty close but not identical to what the true experimental data is. Okay, so we can play around with our Km and our Vmax if we want to and see how that changes things. So I can make Km 100, and you'll see that changes my calculated values, but not my actual values. I can make Vmax 100 and see what that does. Okay, so we can fiddle around with these two values and see if we can come up with the best possible fit. And that fit is going to be indicated by minimizing this value, which is the sum of the error differences. Okay, but doing that manually is a pain. So what we want to do is leverage the tools that Excel has available to do this for us. And that's where the solver tool comes in. So first things first, you want to make sure that you have solver installed. That's under Files. You can go down to Options and click Add-ins. Once you do, on the bottom here you have an option to manage your Excel add-ins. So go ahead and click Go. You want to make sure that you have the solver box checked and then click OK. And when you do, you're now going to have the solver tool that comes up under the data tab all the way to the right side under solver. Okay, let's go ahead and open that. So when we open it, what we want to do is set our objective to this sum of our differences. And we're going to minimize that by changing our estimated Km and Vmax values. Okay, so our objective is I9 in my case, so it's the sum of the differences, the sum of the errors. We want to minimize that value by changing the guessed values of Km and Vmax. And if we do that, I'm going to click Solve. What you see is it updates these values, so Km is 100 and Vmax is 75. And you'll also note that in our graph here, we have a perfect overlay between our calculated values and our actual experimental values. So in this case, Km is 100 and Vmax is 75.